So I noticed that some of you had some questions about the Hardy-Weinberg problems in the study guide. I wanted to redo the violet problem a second way because oftentimes you can do these problems more than one way. So in the video that I posted, I used Q to calculate Q squared in order to determine the frequency of the homozygous recessive genotype in this population of 500 plants. But I want to show you that there's another way we can do it. So the first step we're going to use is to determine which equation to use. And in that problem that I worked out in the video I posted in the study guide, I used Q squared plus 2PQ plus P squared equals 1. But I want to highlight in this video that you can also use the other Hardy-Weinberg equation, which is P plus Q equals 1. And that's just so logical when you think about it. If you have two different alleles in a population, then of course the frequency of each of them is going to equal 1. They will be all of the alleles in the population. And remember that P is the frequency of the dominant and Q is the frequency of the recessive allele. So in this problem, we are told that Q equals 0.2 and we're going to solve for P. So P plus 0.2 equals 1. So it's pretty simple to solve for Q. We're just going to subtract 0.2 from 1. So P equals 0.8. So now we know the frequency of both of these alleles, and we can get to answering this question. So if Q equals 0.2 in a population of 500 plants, how many would you expect for each phenotype? Well, if you have P and Q, it's really easy to plug them into the other formula, P squared plus 2PQ plus Q squared equals 1. So remember that in this formula, P squared is the frequency of the homozygous dominant individuals, and 2PQ is the frequency of the heterozygotes. So we're asked about phenotypes here. So these are going to have the dominant phenotype, and these are going to have the recessive phenotype. So what I'm going to do here to solve this problem is to take Q squared and multiply it by 500. And then I'm going to take P squared plus 2PQ and multiply that by 500. So I know Q is 0.2. So Q squared is going to equal 0.2 times 0.2, or 0.04. So 0.04 times 500. That is going to be the frequency of the recessive phenotype in this population. And just like we solved before, that's going to just be 20 individuals. So we have 20 individuals with white flowers. If we want to solve for the number of individuals with violet flowers, we're going to take P squared plus 2PQ, and we're going to multiply that by 500. So P squared is going to be 0.64. So that's 0.8 times 0.8. And 2PQ is going to be 0.16 times 2. So that's 0.32. So if we add these up, we're going to get 0.96, which makes sense because we know that p squared plus 2pq plus q squared has to equal 1, and this was q squared. Whoops, this is supposed to be a 6. Let me erase that. 0.96. And we know that 0.04 plus 0.96 is 1. So now all we need to do is multiply that by 500 in order to come up with the number of individuals with the dominant phenotype, which is violet flowers. So that's going to be 480. So, as you can see, I think the way that I solved it in the initial video was a little simpler, but you can also get to this by solving for both P and Q first. I hope this helps clear up some confusion.